As Mike said, I think it's cool when folks get an opportunity to talk to, learn from, hear from a variety of people on staff. I think it's like a strength of the design of Turing where it stands now that most people uh, will typically learn from about like 12 or 14 different staff members over the course of their 4 mods. And uh, I think that's great because there are some people you'll like really connect with their style and their approach and their interests, and there are other people where you're like, I never know what that person's talking about, and that's okay. Maybe not all the way don't know what they're talking about, but some people click and some people don't, and I like that you get to have a variety of that. Back in the day, it was just me, and like 2013, I guess I had a co-teacher, so it was two of us. We taught the whole thing 6 months every day. And also, we didn't know what we were doing. So we were like planning the lessons in the morning and then teaching them at 9 o'clock and then debugging from there. So thankfully, we generally don't do that anymore. People have all these curriculums and plans and project specs and things that have been iterated on and all that. So that's great for the most part. And I think the approach that we have towards like teaching and education and so forth is really rooted in skill development. And most education is not about skill development, it's about like knowledge acquisition. And the way you teach like knowledge acquisition and skill development are pretty different, or should be different. Skill development is very like practice driven, right? So let me give you a little bit of knowledge, a little bit of process explainer, and then have you execute that process, learn from executing it, and like get better at that skill. Knowledge acquisition is more like, let me deliver this information to you so you can memorize it, and then you can decide what to do with it later. So most all of what we do at Turing is like skill development. And this is not one of those days. So I don't expect you when we get done to be designing computer hardware. I don't expect you to be experts on these topics, but I hope that you're like a little bit interested in them, have some exposure, maybe have found some things that you want to look into more, or even just that you might like reconnect with later, whether you're working on a project or you're in job interviews or you're in the job itself, doing your continuing education, etc. And one of the inherent disadvantages you have as a Turing student is that the majority of you have not been in and around programming, computer science, computer super nerd world for like a decade or two. And when you're in those spaces, you pick up a lot, like a breadth of shallow knowledge. And shallow knowledge is not super useful in terms of like applying to a job or applying to work, but it is useful for discovering which might be your thing and what you might be interested in. And I always worry a little bit with Turing students. It's like, we're going to teach you this set of skills, this set of understandings, and we're going to go deep on it. But if we don't develop any breadth of exposure, then you don't know what's out there that you could learn, or you don't know what's out there that you could get interested in. And what about things like cryptography has always been one of my like passion subjects in computer science. And like, so let's find a place to like talk about that, even though it's not going to be the focus of your jobs. It's not going to be the focus of the program, but let's like shoot off a firework that says like, here's what cryptography is. And like, maybe you think that's really cool and one day you want to follow up on it, or here's what this other idea is, and kind of allow those to be in the periphery. So today is one of those days. We're going to talk about how computers work and kind of like how electronics work, and stitch that together into some bigger ideas. I'll say that there is a way that I've taught this class about 16 times or so. And today I felt like doing it a different way. So we're going to talk about different subjects. We're going to talk, like, go through a different path. Maybe we'll hit some spots that don't make sense. It'll probably be okay. I'm not like too worried about it. I'll also say that while it is possible for me to talk to myself for 2 hours, and I may or may not do that on a daily basis when y'all are not here observing me, I would love to get your questions along the way. And it's very unlikely that you're gonna like mess me up or throw off the timing or whatever. And I'm definitely not gonna be like, you dumbass, how dare you ask that question? Worst case, I'll be like, I can't get into it right now. Like, that's too deep a dive or something, or I'll put it onto the parking lot. I do have like a sequence of steps that I want to kind of go through. I'm hoping that we can get through all of it, because I haven't taught a lot of these things before. I don't know how long they'll take, so it's kind of a guess. We will take some breaks. So I'll say that between now and 10 o'clock, we'll take at least 2 breaks, maybe 3 if it feels right. So your goal for this session, I would like really appreciate it in a way, like it would warm my heart if you would take notes. And I hate the idea of like telling you all kinds of stuff and then you go like, oh yeah, great, and then it's just kind of gone, you know, and like tomorrow you can't come back to anything, you can't remember anything, whatever. I am going to be drawing, so I have a lot of markers, and you might need a lot of markers. Our good friend Amy Holtz always gives me a hard time because I will leave the caps off the markers during the class. And so if marker murder offends you, then I apologize in advance. I get paid enough, I can buy more markers. So if the markers die, there will be more markers coming via Amazon tomorrow. But so far, I think these are going to be okay. And so I would just, yeah, love if you would like take some notes and do some drawings along with me and like draw some questions. And you don't have to be a good artist. You'll find out I am not. That's okay. We're engineers, so we don't have to be good artists. If you are a great artist, then kudos to you. And maybe you can draw some better pictures than me, and then we can pretend that your pictures are my pictures. And I can co-opt your artistic skills. That would be fabulous. No, I wouldn't do that. So draw, take notes. This is a topic for exposure. You're not supposed to understand everything. You're not going to be tested. This is not like mastery driving material. I did click record on this, so thanks for the reminder on that. Some staff members may drop in, like Ian's here for a little bit listening in. Yeah, I think that's kind of it for my framing. Like, any questions about the big picture? I'll try and keep an eye on the chat along the way, but also you can just like unmute and shout your questions at me. I'm not gonna cry. All right, well, cool. Let's do this. Let's go screen share. Oh yeah, I have to tell you another thing, another pre-thing. All right, so this is my desk, and this is my paper. I think you can see me and the desk at the same time. Okay, now, as some of you may know, Denver Public Schools is about to start school next week, and we're in the process of converting our garage into a schoolhouse. Okay, so took the garage, installed insulation, put in new windows, put in drywall, new electrical, painting this weekend, subfloor, all these things. And one of the things I did was some spray foam around the new windows. And some spray foam got on my fingernails and it won't come off. And it's been like 2 weeks. So you're gonna have that's this. So when you look at my hand and you're like, the fuck? I apologize, it's spray foam. I've tried to get it off. One day my fingernails will grow out. I'll just keep them like this. have always been this weird, in case you were wondering. So, let me see. I guess I'll give you a little like quick background. I started teaching. I did undergrad in computer science, computer systems engineering, it's called, which is a blend between electrical engineering and computer science. Graduated from Arizona State with that degree and a degree in economics in 2003. I went on to teach middle school for 1 year, high school for 4 years, and then helped run a middle school for 2 years. And a lot of these topics are things that I actually learned more in my teaching than I did in undergrad. Because I was looking for like ways to explain computer science in like interesting ways. Also myself, like I'm just a pretty curious person, so always digging in to try and figure out how things work. When we, oh, dang, some podcast shout out. Code Newbie. That was a while ago. That was a minute ago. One of the things I was thinking about this morning is when I was a little kid, I really loved magic tricks. I'm going to hope that this camera will stop like freaking out on its focus, but we'll see. When I was a kid, I loved like magic sets. I didn't really have the discipline to practice magic tricks to make them like good, but I loved for my birthday or Christmas or something getting those sets of like 40 magic tricks because I just wanted to see like how they worked. And then the performance part to me was like not compelling. I guess it's not that relevant. I was a street performer later, but not doing magic. So this idea of magic to me is really interesting because I think at the heart, like engineers are magicians, not that they like create something out of nothing and like have a big debut, like a big splash. It's that engineering is often about creating illusions. And when we talk about computer science and electronics and so forth, there's a lot of illusion building. And so today I want to like frame how computers work under this idea of illusions. And we're going to start with like a very humble piece of the puzzle. Okay. I'll say I'm not going to use colors in like a particularly meaningful way. It's not like blue means this and black means that or whatever. It's just not that serious. Okay, so this is where we're going to start for how electronics work. A little square, 2 lines coming out, 1 line that is going to be the plus and 1 line that is going to be the ground. Okay, this is our light emitting diode, which is an LED. Okay, light, you know what that is. Emitting means it comes out. Diode, a diode in an electrical system is like a one-way gate. So electricity can go through it, but it can't come back through it. Your veins have effectively, like, I forget what they're called, but they're a shape that works like diodes, like it allows your blood to only flow one direction. Is it called valves? I think there might be another name, but they're like in the vein, they're shaped like this. So like blood can go through, but can't flow back. A diode in an electrical circuit allows electricity through one way, but doesn't allow it to come back the other way. So a light emitting diode, when a voltage is applied here, then it lights up, right? So voltage, whenever you talk about electricity, you have voltage and amperage. Okay, so voltage is expressed as a difference in electrical potential. And voltage then, because voltage is a difference, it has to always have two measurable points. Okay, it's kind of like saying, what's the height of a thing? Well, the height has to be relative to something. Or like, what's our altitude? Our altitude has to be relative to something. Altitude is a difference, like 5280 above sea level, but my altitude above my floor is 0 because my feet are on it right now, right? So voltage in the same way is difference in electrical potential. In most computer circuits and like electronics and so forth, you're dealing with voltages around 3.3 volts to 5 volts, also 12 volts. Those are like the typical voltages in electronics. If you were out there with me wiring up the garage, you'd be dealing with 110 volt is like your typical wall power for your like washer dryer type situation, or if you're in some other countries, you might have 230 volts. And then amperage is we're going to call it the actual power flowing through a circuit. Okay, and so in order for an LED to be activated to shine light, you have to apply a voltage across the two wires, and that electrical current has to have enough amperage to actually power it. So you could have a voltage of 5 volts, but have an exceptionally low amperage, and it wouldn't be enough power to make it light up. You could have a lot of amperage and the right voltage, and the LED would just use what it needs, and then the leftover amperage would just go out into the ground. You could have a lot of amperage but too low of a voltage, and the light will not light up. So this is relevant. Like a side note, if you're ever looking at plugs and you're trying to find like a plug that matches some device, you're like, I don't know, you have some electronic thing and it's got like a barrel plug on it, but you've lost the correct power plug. You can look at the label and it'll say like 12 volts, 1.5 amps. And you can look through your miscellaneous bucket of plugs that have been discarded from other things. And you have to get the voltage right, but the plug, the wall plug needs to have a minimum of that amperage. So if it says 12 volts, 1.5 amp on the device, and you find a plug that's like 12 volt, 2 amps, you're good to go. But if you have 1.5 amps and 5 volt, no, it will not power on. So like you got to match voltage, amperage, you can have more, you can't have less. Okay, so an LED, you put the voltage across it, it consumes some amperage, it's turning that electricity into light. Cool. So now just having a light that's on all the time is not that useful, right? So if we were in our house, we might install a switch and switch it up. Now you connect the circuit, switch it down, you don't connect the circuit, you disconnect the circuit. A switch in electronics is usually drawn like this. Okay, so now my plus is here. I'm just going to go ahead and draw this through here. And when the switch is closed, which means like connecting it here, then it's like the switch doesn't exist. The positive flows right into the LED and comes through. When the switch is open, then it's as though the wires are disconnected and no voltage, there's no voltage present across the LED, so it doesn't light up. You will have seen before, okay, so so when it's off is also called open to an engineer, which is like this, okay, and on is really called closed, which is like this. And the place that this idea is relevant to you is often you will see on power switches of electronics. Do I have anything here? Nope. you'll see on switches a circle and a line. Or if it's, that's like a toggle switch. If it's like a single button, like on a computer, it might be drawn like, it's fucked up. Do like this. Or you could draw it the other way. Okay, and all of these are to indicate that they are electronic switches. This, you remember this O is open, and the line means closed, and closed means on. This means that it is like a, not a momentary, but like a push button. Either one of these, that they're both a line and a circle together. Okay, so you have switches, control your LEDs. This might be like the most valuable thing you learned today, is like what those symbols mean on those switches, so you could get it right. All right. So if we control LED this way, what I want to build towards is thinking about like a monitor or a television. And a TV has like approximately a bajillion LEDs in it. So you could wire up each LED to a physical switch and have a very sad person sit there and jiggle switches back and forth and like make pictures show up, but obviously that can't work. Physical switches are loud, they're big, they don't work that great. And if you wanted to wire up like a 4K TV, I don't even know how many LEDs are in there, but it's a lot. Just the switches, even at the tiniest level, would be building size. So in the 20th century, there's like one of the most important innovations is, yeah, I can explain, Curtis, I'll look for a shot about relays. We can talk about relays work too. In the 20th century, there's research, engineering work happening around these idea of switches because we need to make things smaller. Smaller things generate less heat, they waste less electricity, you can fit them physically into smaller spaces, but they like really, the smaller electronics get, it really changes the game in terms of how they can be used. So there's this innovation that took me, honestly, a long time to understand. And I'm going to explain it to you the way I get it. Okay, and let's see, I'm going to need some more colors. Let's do like this. Okay, and this is called a transistor. A transistor is an electronically controlled switch. And if we have electronically controlled switches instead of physically manually controlled switches, then this opens the door to doing all kinds of like automations and connecting transistors to transistors to transistors in like creative ways in order to create complex circuitry. Right? And so the transistor underlies like every piece of electronics that you use today. And the way it works is like this. You have an input side and an output side. Here you have a control. And inside is where the real like genius of this takes place. A transistor is made of silicon or silicon, but really it's silicon, but we say Silicon Valley, whatever. It's silicon is the correct way to say it. And silicon is a non-conductor. It's an insulator. Okay, so paper is an insulator. Like if I put one live electrical wire on this side and put a wire on this side, no current would pass through, right? If I touch them together, or if I used like the metal of my clip here, it's a conductor, so the electricity would pass through, right? So silicon is an insulator, which means it does not allow electricity to flow through. Where it gets interesting here is a technique that is awkwardly called impregnation, where you take silicon, and you impregnate it with copper molecules, okay? And so you take this silicon and you put some copper, usually copper is orange, so I'll find an orange here. And at like a really tiny level, you just spray copper all throughout the structure of the silicon, okay? Now you have an in-between kind of thing. You've created a new thing because copper is a metal, is a conductor. Silicon is an insulator. Now you have a conductor and an insulator mixed together, and specifically you can manipulate that behavior so that it behaves as a conductor sometimes and as an insulator sometimes. This is what is called a semiconductor. It's like neither a conductor nor an insulator. It is in between, and specifically that it can be controlled to behave as either one at some times. So in a transistor, when the control value is low, when there's no electricity on this control line, and I guess you could reasonably say, hey, you said voltage has to be across two things. Good point. Put the ground on here. Okay. When the control is low, the internal structure of the transistor looks basically like this. These copper molecules are all scattered about. But there's an important part here, which is that along this area, there's basically a sheet of copper, okay? And then in here, I think you can see this, okay? There's a little stub of wire, kind of like this. Okay. When the control is low, there's no electricity, copper molecules scatter all over the place. Now it changes. Got our input, our output, our control, our ground. Okay. Now when, that's a CTL, not CH, control. So when we apply a voltage here, let's say that I need a little contrast. How about this? Okay, let's just say that this is now high, which means there is yes voltage on that line. What happens internally is that the copper molecules in this semiconductor move. And they move like the tiniest 1 bajillionth of a hair or whatever, okay? But what happens is that instead of being scattered all over here, when you have a voltage on this line, it's connected to this top line, okay? And voltage or electricity and magnetism are like intertwined. You can't have, like whenever you have voltage, you have electricity. Whenever you have electricity, you have magnetism. Whenever you have magnetism, you have the potential of creating electricity. So there is an electric field generated when you have any wire. Let's say you have a wire with voltage like this. It creates a magnetic field like this. Okay, and now given my amazing 3D art skills, this, for a wire going my left to right here, the magnetic field is this direction, coming like out of the paper. This is Z-axis here, okay? So when we put an electricity, when we apply a voltage to this control line, what happens is that it creates a magnetic field this way. Okay, and all those scattered about copper molecules or ions or whatever the fuck, little bits of copper, they are ferrous. They're like attracted to magnetic fields. And so all of them get pulled up towards this control line. And what happens is they like distribute themselves evenly because they all try and like shoulder each other out like students trying to get free pizza. They all like get shoulder to shoulder as close as they can get. There's like a little impermeable line of silicon in between there, but they get as close as they can to that electronic field. And so rather than being scattered all over the place, they're now lined up really, really tightly all the way across. And what happens is now you have created effectively a wire where there was previously nothing. So now there's wire here, there's wire up here, this stub, and now electrical energy can flow like hopping from copper bit to copper bit to copper bit to copper bit across.
Hey Jeff, how do the copper molecules move through the silicon?
Yeah. I don't know. But the movement creates friction, and that friction is why electronics get hot. So like when the current is applied, they move, you know, and we're talking like, yeah, like molecular level movement, like teeny tiny, beyond my expertise movement, but moving. And then when so they move to form that line, when the voltage is removed from the control, then like molecules tend towards chaos, they spread back out into this like cloud shape. And so that like movement towards the control, moving away, towards away, it's just kind of like rubbing two sticks together. And that's why you get heat from electronic systems. So when you have a control line, now you have a wire. When you have voltage on the control line, you have a connection between in and out. When you don't have voltage on the control line, you do not have a connection between in and out. And so what's the implication of this? It's easiest to express in what we would call a truth table. And truth table is going to go like this. We'll say we have an input and a control and output. Okay. For we could say let's use the same words I used over here. I guess I'll try and use the same color. Okay. It could start out that the input is low, no electricity, and the control is low. Okay, so if the input is low, if the control is low, then there's no connection. So if there's no connection, then the output is necessarily going to be low. If the input has electricity and the control is still low, okay? If there's electricity coming in here, but control is low, it doesn't matter. The electricity from the input can't get to the output if there's no connecting wire, so that output is low. Here, if the input is low and the control is high, so control high, now we have a wire, whatever is on the input comes out the output. So input low, there is a connecting wire, input low, you still get low out. And control high, input high. Okay, so if there is a wire and there's electricity coming in, now you get electricity out. Okay, if we come back to the idea of like physical switches, we could say, consider like the input being the voltage coming into your house, like the electricity into the place that you live. If the electricity is off and you flip your switch for your lights, too bad, you get no lights. If your electricity is on, but you turn the switch off, you also have no lights. If your electricity to your house is off, but you turn on the switch, you get no lights. If the electricity to your home is on and you turn the switch on, then yes, you get lights. Okay. Instead of high and low, it's kind of hard. It's like a lot of letters to write. Okay, so we might express this as input, control, and output. And we could do this like this with T's and F's. Go here for true and false. So low is going to be false, false, false. True, false gives me false. False and true gives me false. And true gives me true. Okay, so question for you is, look at this scenario here, and this is now what we're doing here is like electrical logic. What kind of logical system is this? Or like, yeah, Jake, say more, say it like out loud.
It's an AND operator.
Yeah, it's an and like function, I would say, right? Where the output is only true here when both inputs are true. If either input is not true, then the output is false. Okay, so the transistor is on its own, functions as an and operator or an and gate, we would say, in electrical systems. The part I'm not going to get into here is that you can now take this, once you have an AND gate with these 4 wires, including the ground, you can rearrange the input, output, and control to wire multiple AND gates together to create OR gates and NOT gates, and then NAND, which is not and NOR. So you can build off of this idea, you can build, so your AND is already done. We always write them in all caps. AND, OR, NOT, NAND, NOR. It's also XOR, which is exclusive OR. Okay, so these are like all the fundamental logic gates that you would exclusive and I don't know about that, Ian. I think Ian might be trolling me. These are the fundamental gates by which you can build all electronics. Okay, and so they're all built from transistors, where the transistor is effectively an AND. You get the AND for free, and then you can, if you're interested, you can look it up on Wikipedia, like different diagrams of how you connect. Some of them are like 7 or 8 transistors. Like it's not a trivial rewiring. But given this transistor, you can build all these logical functions. When we talk about like, oh, this Pentium processor has 3 trillion transistors in it, and you're like, is that necessary? Do we need so many transistors? Like, that's why, because it's all built up, like the whole functionality is built up from this little concept, little teeny tiny AND gates put together in crafty ways to create more advanced technology, right? So like everything from your fridge, your TV, your computer, iPhone, whatever, like all of those things are at the core built on transistors, which are just AND gates stitched together in very fancy pants ways. Is that the part that to me is like the most fascinating here? Like these parts are like really useful from a science standpoint and engineering. This is the part that took me a long time, and that once I understand it, I was like, oh shit, that's cool. Does it like make sense the way I explained it, as far as this kind of cloud of copper becoming the wire thanks to the like magnetic field, and that when the control gets turned off, that it scatters back out?
Hey, Jeff,
Yeah.
what determines whether the control is low or high?
You as the engineer, right? And it's probably some previous transistor in the system. And so that's kind of where we're going to get next, is like starting to stitch some of these things together into more complex ideas. Does that make sense? Cool. All right. Let's take a quick break right there. Finish transistors. And I got 9:43, so let's pick up at 9:49.
I did have a quick question.
How dare you, Jake? Yeah, make it quick, go.
So you said the friction is what creates the heat.
Yeah.
But doesn't the friction only come on when you're going from off to on?
Yes, but because there's like a trillion transistors, that they are going off and on all the time.
Okay.
So it's like everything that we do from here forward in this conversation is going to be starting to explain like why these transistors are like nonstop, faster than you can comprehend. They're turning on and off constantly. And so it's like if my kids have like a light switch rave, tick, 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 like just flipping on and off faster than you can comprehend. Cool. 4.5 minutes. Be right back. All right, so we talked about transistors and LEDs. Let's start to like stitch it together into some little bit bigger ideas here. So, okay, with the LED, we said like LED has on and off. Put light out, don't put light out. If you, let's say we have 3 LEDs, and an LED construction is like the diode is inside a plastic, and that plastic could be clear, it could be like cloudy white, it could be colored, right? So if I make a diode with a red plastic, a diode with a green plastic, and a diode with a blue plastic, internally, same construction. It's just the plastic shell that's different. Okay. Now, each of these is going to have a ground. I could put those all together. Grounds can be shared. Okay. And then each of them is also going to have a signal wire. I'm going to use this kind of magenta here.
So what you're drawing right now is just a few different LEDs.
Mm-hmm. Okay, So I've got my red, green, green, and blue. Okay. So if I put 3 LEDs together of these 3 not primary colors, but 3 colors, now I can start to do interesting things with them, right? If I apply a voltage to red, and I'm gonna, let's see, I'm gonna do this. I'm gonna use ones and zeros. 1 to mean yes voltage, 0 to mean no voltage. 1 means true, 0 means false, 1 means voltage, 0 means no voltage. If I now say put voltage on the red, I leave no voltage on the green and no voltage on the blue, then what am I gonna see? Red. Okay. If I put no voltage on the red, voltage on the green, no voltage on the blue, I'm going to see green. If I have no voltage on red, no voltage on green, yes voltage on blue, I'm going to have blue. Okay. Now, this is where I'm going to need you to help me out because I'm colorblind. So we're now entering my area of non-expertise. If we put 1, 1, 0, so we have red and green together, what you gonna get? Like purpley, yellow, red, green, yellow. Okay, great. And if we have no red, but we do have green and we do have blue, you can speak, you can use your words. Teal. I realize now maybe I should fact check this, but okay, we'll go with teal for now. Doesn't matter too much. We've
I have
also
a quick
got
question.
Question me.
Why is it RGB? So why is it red, green, blue instead of the primary colors of red, yellow, blue?
Yeah, I don't know. My guess is that it probably is like a manufacturing detail, that like green is cheaper or easier to manufacture than yellow, or that yellow like fades over time and green it's easier to keep it like staying the same shade of green, or like something along those lines. Not I don't think it's like a idealistic choice.
Jeff, it's because how our
Go
Do it.
ahead, Aiden.
Oh, go ahead.
Give me the same answer.
Go ahead, go for it.
okay, yeah. So it's because of the different way that light works in additive and subtractive ways. So monitors are additive, which means that when you add the light together, you get colors, and when you paint with things, it's subtractive because it's subtracting the light that's bouncing off to your eyes. So when you have your red, yellow, and blue on your paper, it makes a difference between when you add it in on a monitor. The red, green, and blue interacts directly with our eyes, with our cones in our eyes. Those are the colors that are most easily differentiable in. Yes, I was Garrett. In the easily the red, green, and blue are the colors that are easiest for our cones to differentiate and send different signals to our brains. So basically, monitors are hacking our brains into believing that everything is not just red, green, and blue.
Thank you. Yes. And so this is where we get into the idea, like mentioned earlier, about like illusions, right? So if these LEDs are red, green, and blue, they like there's no such thing as white. Or like when we look at a TV that doesn't have white LEDs, but we create them by turning the red and the green and the blue on. and you get white. So wait, that's subtractive? That's what I said?
Well, monitors are additive.
Additive, okay.
Because when you don't have
Yeah.
any lights from the monitor, it's black. So-
Yeah, okay. And you got any thoughts on red and blue together?
That would be magenta.
Sure. Okay. So we could combine a red, a green, and a blue to create a whole bunch of different colors. Whether these are exactly right colors, doesn't matter. Just understand that there are several different colors here. And there's one left off, which is 000, which is black. Absence of color. Okay, now these are in kind of like a chaotic order. If I was going to write them in the right way, it would go R, G, B, okay, and you go 0. I do slash my zeros, and you should too, because they're not O's. Okay, 0, 0, 1, and you'll think that's stupid until one day you debug some software where someone has put an O in place of a 0, and it will happen to you. Just like the day that you spend many hours debugging the fact that you misspelled initialize, because instead you said initialize, but that's not going to help you. If you say initialize, 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 you have a chance of spelling it correctly. 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. This is the typical way to write what is now binary here. And so these binary numbers, binary meaning that they are made up of only two symbols, either 0 or 1. Okay. We have only zeros and ones here. These are equivalent to some decimal numbers. Of 0, 1, 2, 3, 4, 5, 6, 7. Okay. If we have 3 LEDs, now we can create 8 different colors. Okay. They are in a certain order just by our preference, right? If each of these colors maps, if each of these combinations maps to a color, 000 was black. I'm just going to put the ones that I'm actually sure about. But white, the solo red here, the solo green, and the solo blue. Okay, and whatever other colors these are. Maybe these are right. This is now what we would call the color depth of this system, like how many different colors this system of 3 LEDs can display. Some of you are what I would like to call real grown-ups, like over 30 years old. And you may have played a fantastic electronic called a Nintendo, original Nintendo, and we would say Nintendo was 8-bit, quote unquote. And then you were like, Super Nintendo, 16 bits, more bits must be more better. And like Nintendo 64, 64 bits, let's have infinity bits. Whatever the bits are, the games seem to get more fun. It doesn't exactly work that way. But to say that Nintendo was 8-bit is that the color palette was 8 colors. That every color in the images that were drawn was one of these specific 8 colors. Okay. So you use a single LED, you combine them together into triplets, and now you have a depth of 8. Now let's go a little bit different direction. What if you had, instead of a red, what if you had, let's go like this. Let's go 2 reds and 2 greens and 2 blues. Okay, and they all shared common ground. I'm not going to draw the ground just because it makes it unnecessarily confusing. But we have R1, actually, yeah, I'm going to call that R1. I'm going to call this R0. I'm going to call, I'll just do this like this. This is going to be G1, and God, come on, man, with the arrows. G0, and this is going to be B1, and this is going to be B0. Okay. Now, if each of these lights can be controlled independently by their own control lines here, then our minimum possible value, our black value, would be 0, 0, 0, 0, 0, 0. Then our next value up would be to have some blue, half blue. Okay, and these would be all zeros. Then we could have like this. Now maybe if these are actually exactly the same, now this color and this color look exactly the same. But if there's like maybe a teeny tiny variation between them, you could get some different shape. Okay, then we go 0, 0, 0, 1, 1 for like a more vibrant blue, like a brighter blue. 0, 0, 0, 1, 0, 0. Okay, and now we start to mix like green and blue like we did before. I'm not gonna do the whole tree here because that'll take a lot of drawing, but let's skip ahead a little bit. And let's say we've got maybe like 1, 0, 1, 1, 0, 1. And so now we have like twice as much green and some red and some blue. And so across these like 6 bits now, we would have twice as many variations of color. Okay, so they're all going to be like these same 8 colors are still going to pop up in here. It's just that in between each step, there's more finer and finer gradations. All right, so the color depth, we go from black to white always. When we get to the end here, 1, 1, 1, 1, 1, 1, you still get white. The more bits we have, the finer steps we can take in between. Okay. So then these all become numbers, and I believe the way it's done is that we also have another 2 bits that are like, you can do it with transparency as an additional 2 bits, or I think you can do like intensity with 2 bits, but even though we have like 6 lines here, we'll add another 2 bits to get 8-bit color. It's not RGB, it's like adding intensity or transparency or black or whatever. Okay, and of those 8 bits, if the minimum value is 0, 0, 0, 0, 0, 0, 0, 0, and the maximum value is 1, 1, 1, 1, 1, 1, 1, 1, we can do this more conveniently in some other number systems. So 0, well, no matter what your number system is, that's 0. If you choose to use decimal here, then this represents 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, which is, you add all those together, and what you get is 1 less than 2 to the 8th, which is 255, right? Pretty sure. I'm sure you'll tell me if I'm wrong. Okay. Decimal and binary, it's kind of hard to move back and forth between them. But when you use number systems that are powers of 2, it's easier to move between binary and those systems. So specifically hexadecimal, this would be decimal. And in hexadecimal, this would be FF. And so then you're like, hexadecimal, that sounds like a cool word. That's interesting, Aiden, an extra red and green, just to get more shades in there. I think it can vary, like, I think it can vary by system how those last 2 bits are used. Like, I believe when you talk about like web colors and so forth, that if you make it 8 bits, that the last 2 are around transparency, but like Nintendo didn't have transparency and so forth. Okay, so hexadecimal goes like this. Quick primer on number systems. Binary means that you only use 0 and 1. And so the counting in binary goes like 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, and then 1, 0, 0, 0. Okay, in octal, you use the symbols, really like trinary and so forth, like technically exists, but there's never a reason that anyone uses those. Octal, you have 8 symbols, 0, 1, 2, 3, 4, 5, 6, and 7. And so counting with those, you would go 0, 1, 2, 3, 4, 5, 6, 7, but not 8. You don't have an 8 symbol. After 7 is 1, 0. And then 1, 1, and 1, 2, and 1, 3, and 1, 4, 1, 5, 1, 6, 1, 7, 2, 0. Okay. In decimal, where you have your full set that you're accustomed to, 0, 1, 2, to 8, 9, you would go 1, 2, 3, 4. Sorry, it's not going to be exactly parallel. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. And in hexadecimal, is what we're interested in here, is we have 0, 1, 2, 8, 9, and then after 9 we keep going. So hexadecimal, hex being 6, decimal meaning 10, hexadecimal has 16 symbols, decimal meaning 10 has 10 symbols, octal meaning 8, oct meaning 8 has 8 symbols. So you have 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you also have A, B, C, D, E, and F. Okay, so here in my counting, that's confusing. That's why it didn't line up. I forgot the 0 on that one. Come on, buddy. Okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so this is like now up to decimal 15. And then we have 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. Okay, so F is equivalent to 15 in decimal. And FF, if you kept these lines going, you get out to 255 decimal, you would have FF in hexadecimal. And so why we use hexadecimal is that for the main reason we use it is that it's an easier way to move. It's an easy way to represent binary, where moving between binary and decimal representations is hard because 10 is not a power of 2. Hex, we say it's easier to move between binary and hex. Let's see if I can do this correctly. If we have some binary number, let's go 0, 1, 1, 0, and 1, 0, 1, 0. Okay, an 8-digit binary, we would say this is 8 bits. 8 bits implies that it's 8 characters of binary, right? Values of binary. Then to convert this into decimal, you have to come back and do this like powers of 2 and add it all up. That's kind of hard. To convert this to hex, you can group them into 4s. And so 1, 0, 0, 0 would be, let's see, 1, 0, 0, 0, 1 triple 0 is 8. And then 1, 0, 0, 1 would be 9. 1, 0, 0, 1, 0, 1, 0 is 10 decimal A in hex. And 0, 1, 1, 0, well, 1, 1, 1 would be 7. 1, 1, 0 must be 6. Okay, so this binary is equivalent to 6A in hex. Okay, so hex becomes a way that we can like represent binary numbers without like losing our minds of just going like 1, 0, 1, 1, 0, 0, 1, 1, like prone to errors and like switching 2 digits around, obviously messing everything up, right? So we can use hex as a way to represent binary. So let's go back here. Okay. Now, let's imagine that we use some of those transistors and we create here, is this a multiplexer or a demultiplexer? I think it's going to be a demultiplexer. Okay, and the idea of multiplexing is to take like multiple streams of input and direct them towards one output, which is like, if you could think of it like plumbing, like in a multiplexer, you're joining things together and sending them out one way. A demultiplexer would be to take one stream and split it out multiple ways. So what we could do here is, if we were drawing up this circuit, let's say this is why did I put the green first? Come on, buddy. Red, green, blue. Okay, And then I also have a second red, green, blue, a third red, green, blue, and a fourth red, green, blue. Okay. And then each of these was connected. We would say they're like addressable, which is that they have an individual wire coming out of the DMUX. Then this demultiplexer could have in it, or have on it, 3 input lines, which we're going to treat as an RGB. My R, G, and B. Oops. Okay. And then each of these LEDs would have an address, and the demultiplexer, you have to like pick which one you're addressing at any given time. And so we'd have 2 control lines here. And so what happens then is this control with 2 bits of control, you have addressable spaces like 0, 0, 0, 1, 1, 0, and 1, 1. And so then these sets of LED outputs, this is your 0, 0 block, this is your 0, 1 block, this is your 0, 2 block, and this is your 0, 3 block. Okay, so your DMUX now allows you to basically pipe this color to whichever one of these you want. Okay, now you might also wire up some additional circuitry in here, like in between the DMUX and the LEDs, which allows the LEDs to maintain their state when the DMUX is not addressing them, so that the DMUX is like changing the state, but if the DMUX switches over to talk to some other LED, that the one that it was talking to previously maintains its state, like keeps showing whatever color mix it was showing.
What are they called again, Jeff?
Say again.
What are they called again? That keeps the color.
That's a good question. You could implement it. I think you would probably put it in the category of like a flip-flop, which is like a basic form of memory that you're essentially building memory into the system so that the LEDs remember what values they had before, and you'd have 1 flip-flop per line, which is like, now that I think about it, a really stupid name, right? But that's what they're called. So then your DMUX would be wired in such a way that when it sends a signal, it would clear the flip-flops of whatever they had previously and then store into them the new values. Okay, but if you didn't have flip-flops and you had it wired up just like this, you could create the illusion of what you want. Let's say that these 4 banks are laid out as like a grid. And so this is 0, 0. Okay. Now, LEDs, like all lights, they take a moment of time to turn on. They don't turn on instantaneously. To you, it looks instantaneous, but it takes a few microns of time. Microns, microseconds, teeny nanoseconds, whatever. Okay. And there's an interesting game to be played here, which is that if you could tell this one, if you could send a signal to 0, 0, and then it starts lighting up, and before it like gets lit or before it can go down, you switch over to 01 and send it its color, and switch to 02 and send it its color, and switch to 03, and then get back to 00 before the voltage has dropped. If you could switch between them really fast, then you would create the illusion that you're speaking to all of them simultaneously, right? And so like you might see this on a failing LED, or like if you use a dimmer on an LED that is not really supposed to be dimmable, like a LED light bulb or something, it's not supposed to be dimmable. When you get to a low voltage, what you start seeing is like pulses of light. And the reality is that like you're always seeing pulses of light. It's just that they're so fast that it looks like constant light, right? And you might have seen this in the past with like CRT tubes, cathode ray tube, like big deep monitors or TVs, where that's how they're working. They're like blasting lines of light over the screen and trying to get back to the first one before it cools off and goes back to black. And so going through there fast enough so as to create the illusion that all of them are being controlled at the same time, but really it's only one single little bit being controlled at any moment. So you cycle through these really fast. You have to also, okay, so you can then start to see how like you could stitch this idea into 2 blocks of 4 and 4 blocks of 4 and 16 blocks of 4 or whatever, and grow this grid of LEDs, and thereby allow you to individually address each pixel is really what you're doing now when you're combining an RG and B. Each pixel on a screen, individually addressable, you can specify the color of every pixel on the screen and control them, okay? Buried in here is this idea of clock rate. And I want to get us, this is going to be our transition from video and images and stuff getting into CPUs and so forth. But let's take a quick pause till, I'm going to say 10:29. And nice axle going through the bucket. It's a little bit off center, okay? And as the water fills up here, it raises the center of gravity of the bucket. And at some point, the center of gravity moves too far above the axle, just a little bit to the side, and now the bucket dumps. Then, so the bucket like pivots on the axle, dumps out its water. Now that it is empty, the center of gravity returns to like its lowest point, causing the bucket to pivot back up to the top and begin filling again. Okay, and so what you have that's so interesting to me about this system is here you have a constant or a fixed flow. And here you have an interval flow. Okay. And if this is constant and you assume like all the physical systems, like this shit's not getting rusted and broken, yada, yada, like wipe all that aside. If you have a truly constant water flow in here, then the interval comes out at the exact same time. It's always the exact same point of bucket filling, at which point it starts to pivot. It takes the same amount of time for that pivoting, and the dump out comes out. Now, you're not changing the water. It's a single source of water coming through, right? Or the water is like conserved in the system, but you're turning constant flow into interval flow. Mike, I was gonna ask you, what's up at 11? We got any flex minutes here?
We can be flexible.
Okay. I think we're probably gonna need a couple minutes. I know that'll shock you. So the bucket machine, the bucket attraction turns constant flow into interval flow. And this is how a watch works also. So when you talk about Watches, you see they're like quartz, use quartz in building a watch, in an electronic watch. And the bit of quartz in there is the bucket, that the battery is flowing electrons into the bucket of quartz. And the bucket of quartz will hold on to them, hold on to them, hold on to them for a period of time based on how big it is, just like how big this physical bucket is. And then every once in a while, every time interval, it will dump those electrons out. Okay, so you can take a battery that is constant voltage, connect it to a bucket of quartz, and get out of it an interval flow, such as, like, you might size your bucket to be 1 second, right? So that the electrons are coming out of the battery, going into the quartz, and that bucket is dumping out every 1 second. And now once you have that, now you can build all the rest of your electronics off of that pulse. If you can count on it coming out every second, then all other timing can be built off of that, right? So if you come back here, you could say, all right, every dump of the bucket, let's change which pixel we're going to. Okay. And now if you made a smaller bucket, it's gonna move faster. Now, if you make a really small bucket, it's gonna go super fucking fast, right? That's great, except that you come back here, and if we start, the faster that we, okay, and when this transistor is in a stable state, when its control is high or low and it stays that way for a moment or two, it allows that component to cool off, to dissipate heat. Every time it transitions, is coming back to like Michael's question from earlier, every time it transitions is when it generates heat. And so if you have a slow clock, things can only move so fast, heat's not a problem. As you speed up the clock, as you get a smaller and smaller bucket, or you fill the same size bucket faster and faster, now your things can transition more, but you have a larger side effect. You're creating more friction because things can change in shorter periods of time. The bucket, like at some point, seems like it's coming out all the time. It's coming out imperceptibly fast, but there is still an interval to it. So by adjusting, so this whole system leads to what's called the clock. Okay, you're creating a clock in the computer that's defining what time means, right? If we accept that like time is a synthetic human creation, whatever, that like our clock in the computer defines what time means. And so every component in the system responds to and acts on that time. If we use a smaller bucket, we can make time move faster, but there's collateral problems to that, specifically in heat. So if any of you ever like try to get more power, quote unquote, out of a computer, you might have overclocked a computer. You might have told your machine, instead of a clock cycle taking this long, make a clock cycle take this long. And the game to overclocking is shrinking your clock cycle so that your machine is going through more operations per your perception of time in the human world. It's getting more clock cycles in there without creating too much heat. So overclockers, gamers and such, like, do all this crazy things with cooling and liquid cooling and fancy fans and submersion cooling and all that stuff. Because if you can keep heat under control, then you can drive the clock cycle way up, your clock interval way down, right? So there's actually interesting research on this going on at like the server level. Like Facebook has like a data center in Greenland, Iceland, someplace I haven't been where it's cold, and so they do geothermal cooling, where they like pipe their heat into the crust of the earth or whatever, and by cooling the machines, they can shorten the clock cycle and get more performance out of them. In any data center where you're operating a bunch of computers, like the HVAC is more expensive than the electricity to run the machines. Like heat is kind of the Achilles heel, is the kryptonite of electrical technology. This time of year, particularly when it's hot all the time, if you have things that don't work well, but normally work fine, it is probably because they're getting hot. I had to go reset like our internet modem because it got too hot the other day, which is sad. Hashtag sad. From a engineering standpoint, like they could have just put a fan in that and then it would have been fine, but instead they like saved 50 cents or whatever per modem, so now I have to go reset it. Okay, so use the bucket, you create a clock. Now that you have a clock, you can start to do some really interesting things. So coming back here to this idea of a multiplexer is like a single purpose circuit. It only does one job. And one job circuits can be useful in a lot of different scenarios, specifically like if we know exactly what the job is. We can use really efficient circuits like this that only do one thing. But pretty quickly, you know, in the 20th century, we transitioned to these ideas of like wanting general purpose circuits or general purpose computing, where we could on the fly program it to do what we want. It's not that it can only do one thing, right? And just like a person, if you do only one thing, you tend to do it like super efficiently, really effectively, fast, all those things. If a system can be built with a single purpose circuit, you do it. Okay. Or if you can dedicate circuitry, if you can afford to dedicate circuitry, you do it. So for instance, like video compression and decompression, the playing of video is historically done in general purpose computers, like going through your CPU. But over the last 10, 12 years or so, video has become so ubiquitous that most devices you work with now, whether it's your laptop or your phone or TV or whatever, they have dedicated circuitry that is implemented just to solve that problem, to take video data and switch it out to these like grids of colors and so forth, right? Thereby alleviating doing the job that could be done on the CPU, but the dedicated circuit can do it much, much better. You might notice this unlike if you use a particular portable device, like an iPad or something. If you watch videos on an iPad, the typical video, like the battery life can be super long, like 8-10 hours. And if you're doing stuff that's 3D rendered, like my kids playing these stupid Roblox games and stuff, it can crush the battery in 2 hours. And it's because the video is going through dedicated circuitry where the Roblox stuff is going through the CPU and like forcing the CPU into 80, 90, 100% utilization for a long period of time, thereby draining the battery. Okay, so let's talk about these general purpose CPUs. So CPU, I'm thankful I caught the flip up on Alex. That was a big sneeze. A CPU is made up of a couple key components. Okay, the most notable is the ALU. We'll come back to like talk about all these in just a second. We have a control unit. We have I/O, and we have memory, which has a bunch of pieces to it. Okay, So there are lots of different models of CPU, but they all like follow this basic principle of these 4 components. So you have the ALU is the arithmetic logic unit. The IO is input output, and it's responsible for collaborating with like your keyboard and your monitor and mouse and all that stuff. Your control unit is like the manager of the CPU, which tells like who to do what when. And then your memory is used for 3 main things. It's used for instructions, or your instructions cache, it's called, input data, and output data, with sometimes output data becoming input data to the next thing. Okay, so every CPU is based around these 4 like key pieces of functionality. The ALU is kind of like the muscles of the system. Like in one way, you could say the ALU does all the work, which is true, but without the data from the memory or the control unit telling it what to do when, it wouldn't be useful, right? So you can make some similar, you can make some analogies to like your human body, where the ALU is like your muscle system, the control unit is your nervous system, activating like different parts of the IO is like your senses, your eyes and ears and mouth on the way out and so forth, and memory obviously like same as your own brain memory. Okay. When you have a CPU, you always have a clock. Okay. The clock functions, I don't know if any of you were ever like rowers, but the clock functions like that person on the front of the boat going, row, 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 row. It's a coxswain, is that what it's called? Something like that? Did I make that up? I don't know. So the clock is connected to this and every component in the system going like now, 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 now. And then it's up to those components to know and decide like what they're supposed to be doing on that interval signal. So the clock talks to CPU, it talks to all 4 of these things. A CPU uses what's called an instruction set. And an instruction set is just that. It's a set of things that the CPU knows how to do. Okay, so the most common one is what's called the x86 instruction set. If you used a 386, well, 286, 386, 46 in like elementary school or something along those lines, those were all x86 machines. Then 586 and 686, we moved into the Pentium name, which that leading digit is what led to the Pent. We never had like a Septium, it just left it with Pentium. And all these chips, CPUs that have been made in the last like 20 years, and the majority of the computers that you've used are x86 instruction set. There are other instruction sets, and why can't I think of the name of it? Well, okay, they fit into general categories, which is like RISC and CISC. RISC is like reduced instruction set, is the idea of like chips that are designed around being able to run less complex instructions, but running them really fast. And sys computing is complex instruction set computing, which is like, let's build more complex instructions that take longer, but then you'll need fewer of them. ARM, that's what I was trying to think of. I don't know what ARM stands for, but like a lot of devices, especially low power devices, are based around like an ARM instruction set. And yeah, all kinds of stuff like, I would expect things like maybe a Fire Stick, like all Amazon's teeny tiny devices, and like a lot of things like that are use like ARM instruction sets. So your focus is on the, yeah, that's true, Aiden. Like, well, it's a transition back to ARM. Oh, that's a good fact, Kate. Advanced RISC. Interesting. So Macs used to run on PowerPC architecture, which is like ARM or like ARM related, and transitioned to Intel because ARM couldn't keep up. Like ARM architectures like weren't, the processing power and speed wasn't going places. And the x86 transition for Apple allowed them to like capture this huge market around like OS 10 and all these apps, and like also it was like an enormously powerful move for Apple. And now they're so powerful that they're going to build their own chips, ARM chips. And I think the belief is that they can do them, make them cooler, and save energy by having that like reduced instruction set. We'll see. I'm not totally sold. Most of our focus is on x86. Okay, so the CPU has these key components, and it runs this x86 instruction set. What is interesting in here is if you combine the idea of instruction sets and clocks, is that what it leads to is every instruction happens in fixed time. Okay. Imagine that I was like a work dictator and Mike was my work receiver, and I was like having Mike add numbers together, right? These instructions are like super, super simple. It's like increment this value by 1, decrement by 1, add these two things together, subtract. It's not like calculus or some crazy stuff going on. It's an arithmetic logic unit. It's not like advanced trigonometry logic unit. Like the instructions are very, very simple. They're just there's so many of them happening that you can create like advanced computations out of it. So, you know, if Mike and I were working together, we're catching up on some accounting and I'm having him add numbers, right? And I'm like, add 6 and 5 and store it in location 12. Add, and then he would go like, okay, I got it. And then I say, okay, now add 12 and 14 and add it, store it in location 13. And then he would give me some acknowledgement back and forth. Like our protocol as human beings would be to exchange back and forth, me giving him a job, him confirming when that job was done. Thereby, I know when to give him the next job. In a CPU, because the instruction set is fixed, okay, the CPU only knows how to do a couple things. It's like the base x86 instruction set is like 60 instructions or something like that. Now, later versions have like extended instruction sets so they can do more things. But these 60 or so commands that x86 includes, we define how many clock cycles they take. And so if I knew for Mike that it takes Mike 3 seconds to add 2 numbers and to store them somewhere, then I could give him 2 numbers in a storage location every 3 seconds, and I wouldn't need any feedback back from him, right? If we agree on the clock, boom, 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 you know, it's a metronome, annoyingly clicking like this, and he knows every 3 seconds he's going to get the next thing. I don't need any feedback from him. I could just dish out work on that expected interval. He's going to complete it on that interval because we've agreed to the clock cycle, and Mike's a machine, so he doesn't have any variation or whatever. So the control unit here can dispatch instructions to the ALU or dispatch like things that need to be sent to IO or captured from IO, and do it all based on the clock without waiting for like feedback. It can go, ALU, do this. Now ALU, do this. Now ALU, do this. And if we know that amongst that instruction set, like this certain instruction takes 3 clock cycles, this other instruction takes 6 clock cycles, this instruction takes 1 clock cycle, now the clock cycle defines how much work fits into like our human time. Accelerate the clock. Each instruction is now executing in a tighter time window, and thereby you get more output, right? So for a long time, through the 90s and 2000s, the grading and what we paid attention to with CPUs was their clock speed. And the higher the clock speed, the more instructions fit in a second of our perceived time, thereby getting more done. So there was 1 gigahertz, and then there was 1.3 and 1.5 and 1.7, and more clock speed meant more better, okay? But then we started hitting this like diminishing marginal returns point, right? Where it's like clock speed over time, like old 486s and stuff, you're running at like 66 megahertz, I think. And so over time, we saw this like, whoa, clock speeds are so great. Oh shit. Okay. And now the reason Apple's trying to make that transition is that clock speeds have been basically flat for about a decade. If you go back to 2010, we had CPUs that were right around this 3 megahertz clock speed. And we haven't really gone anywhere since then. We've changed the instruction set, changed like added some built-in components, some specialized things into the CPU, but we haven't made CPUs faster than about 3 megahertz or 3.2 megahertz or whatever. It's not that they can't go faster, it's that we're not willing to make them go faster, because the faster they go, the more heat they generate. You got all kinds of problems. You got to dissipate that heat if you're building laptops and so forth, which most computing now is done through laptops. If you're building up a bunch of heat in the laptop, that's the problem. You're like melting people's legs and burning them and stuff. And also heat is energy. You're losing energy from your battery into the environment instead of going into your computing, right? So it's interesting with this this curve of like Moore's law, that every 18 months like our compute power doubles, was largely applied to this curve around megahertz. And now the argument it gets like a little bit trickier to make, but what you can say is that now CPUs are progressing on a curve that's not only megahertz, that by adding dedicated circuitry, by adding to the instruction set and so forth, we're still increasing compute power every 18 months. It's just not the speed of it going up every 18 months. Gigahertz, yeah, sorry, gigahertz, I said megahertz. Hertz. Lots of hertz. 3 megahertz, that'd be a very slow processor. Cool. Okay, so CPUs, that's kind of the story on CPUs. Now, the last piece is what we're going to call the application stack or the execution stack. So for you as a software developer, you're like, hey, I'm not doing electrical engineering. I'm not building circuits. Maybe you should, but that's not you right now. Okay, I get you. That's cool. So down here, we have the hardware. And the hardware is made up of the CPU, like the external memory, like RAM, hard drive, whatever. We've got network resources like your Wi-Fi or Ethernet, whatever else, like physical pieces make up the machine. Then on top of the hardware, we start to run some software. There's a really thin layer here called, that we can refer to as the BIOS, which is the basic input-output system. This is a software layer that allows a degree of abstraction across different hardware. So like that allows us to speak the same language, even if you have different RAM chips or different hard drives, like different manufacturers or whatever, that everyone else up the stack can kind of just treat them like hard drive, write this data, hard drive, read this data. And the BIOS takes care of like what instructions has to happen for this specific kind of hard drive or whatever. Then on top of that, you have the operating system. And the operating systems have over time like grown to be incredibly complex pieces of software. But the core job of the operating system is to be the gatekeeper. And what I mean by that is its job is to control access to hardware resources. Okay, the operating system's job is to determine which software gets access to the hardware at which time and for how long, and which pieces of hardware can they access. On top of the operating system, you could have processes. Okay, and processes. A process is not exactly the same as a program. A program is an executable chunk of code. Okay, a process is an executing program. Okay, we'll call it a program in execution. The difference there being that like you could take one program and you could run it. You could run two copies at once. Those would each be, they'd be the same program, but they'd be two different processes. So your process, a process is a program in execution, meaning that it has like code, instructions that it's running through. It has instructions and resources. And the most important resource is memory. That the hardware memory, especially the RAM, that the operating system controls access to the RAM. And when a process starts up, in order to do its work, to be adding stuff, doing whatever magic it's doing, it has to have memory for storing and retrieving that data. And so a process is a set of instructions combined with resources, hardware resources, specifically memory. If you were a C++ programmer, you would write C++ code, you'd run it through a compiler, and that compiler, so let's go like this. You have C++ code, it gets run through a compiler, and what you get out from that is native code. Okay. And native code is what the hardware and the BIOS and like these layers can work with, what they're able to execute. Like you can't run C++ code on a CPU. You have to run it through the compiler to get that native code. So you write C++ source code, you run it through the compiler, you get native code. Now that native code you can distribute, right? So like in a Windows world, this is called like an exe. And yeah, it is like, it's binary or it's like effectively binary, Will, to your question. It's not human readable, that's for sure. Maybe you can like backwards engineer it and with a hex editor and all this crazy shit, but native code is meant for computers. So C++, you compile it, you get the native code. Now that native code can speak directly to the operating system, BIOS, and hardware. And so when you run a native program, it runs in this model. For you as Ruby programmers, if you become JavaScript programmers, Python programmers, .NET, like C#, Java, Elixir, like any other language you can think of, you'll probably, unless you go into systems where speed is key, where that's like hardware engineering, like if you're going to go work at SpaceX and stuff like that, you'll probably learn some C++ and work in C++. If you're going to work in video games, speed is key. You need C++. Pretty much all other computing is moving away from writing native code. And instead, what we have is, I'm going to call it a VMP. Okay, so this VMP is still a process, but what that process is what's called a virtual machine. A virtual machine is a complex abstraction layer that allows for the execution of non-native code in a native environment. So a virtual machine is a very fancy translator. And what that means for you, let's say you're writing Ruby, your Ruby code lives here. Okay. And the VMP, or just the VM, I'm just going to call it a virtual machine. The virtual machine, it plays this translator role, which is that it speaks Ruby to your Ruby code, and it speaks native code to the operating system. It could also be considered like a real-time compiler, kind of, and like a virtual machine definitely has a component that is a compiler. And there's an interesting consequence here, which is how code runs. In a C++ native code, the code talks to the OS to the BIOS to the hardware, okay? And the hardware responds back, and it gets passed like this, it gets passed like this, okay? When you run an interpreted language like Ruby, one that uses a virtual machine, your Ruby talks to the VM talks to the OS talks to BIOS talks to hardware back to BIOS back to OS back to virtual machine, and virtual machine back to Ruby. Perfect native code versus perfect interpreted code. The native code will always be faster. Asterisk, because there's no always in computer science, okay? But let's say it's basically correct that native code is going to be faster than interpreted code because the interpreter adds an extra 2 steps into the sequence. No matter how fast the sequence is, having fewer steps is going to be better than having more steps. Okay, so when you write let's do this part of the diagram up here. You write Ruby or JavaScript or Python or whatever, okay? It goes through to the virtual machine. And the virtual machine on the fly generates native code. This can also be called bytecode. Now, there are some really mind-blowing things to me that have happened in the last 15 years in this virtual machine space, which put the asterisk on the idea that native code is always faster. Specifically, like the most advanced virtual machine in the world is the Java virtual machine. And the Java community, I don't like it. I'll just say that. The Java virtual machine is like unbelievable with the computer science that has gone into that, with things like techniques like predictive branching, which is the virtual machine watching the execution of your code and hello. This is Violet. She says hello. All right, I gotta finish. The virtual machine watches the execution of your code and rewrites your code on the fly to run more efficiently, or executes code out of order because it sees that like every time you go down these steps, you go to this branch, and 9 times out of 10 you go this way at this if statement. What it starts doing is, as it's evaluating the if statement, it starts running the code inside the if, predicting that that's probably going to be the path. And when the if statement condition evaluates and it comes back true, it's already 2/3 of the way through running the code in there. And so it's maybe possible that virtual machines rewrite your code to be faster than you could ever predict it, because it can observe it in runtime where you can only really observe code static time, like reading the code. It's really, really hard to observe the code while it's running. Virtual machine can do that, and thereby like maybe, I would say that over time we'll see virtualized code or interpreted code like swallow the whole world, that video games and everything else will be using these languages. And you see that a little bit already. There's like C# is coming up in the game space. I think Unreal Engine and stuff like that, like you write C#. And so that's how, when you write code, that's how it runs. Like you say at your terminal, like Ruby my program.rb, because you're telling the operating system, run the Ruby process and tell the Ruby process to run my code. So you're telling the operating system, start up the virtual machine, and then it passes this message to the virtual machine of like, the operating system doesn't know what this is, doesn't care. It just passes that message to the virtual machine. It's like, hey, somebody asked about myprog.rb, and the virtual machine goes, oh, okay, I'm gonna look for a file with that name in this directory. I'm gonna load it up and start real-time compiling it, executing it, and telling you what I want to happen. As far as the operating system is concerned, the Ruby code doesn't exist, only the virtual machine exists. As far as the Ruby code is concerned, this is the beauty of interpreted language, is that the Ruby code doesn't care what happens underneath the virtual machine. So you can write Ruby, you can write Python, you can write C# or JavaScript and run them as long in any space where there is a virtual machine. So if your refrigerator has a Ruby virtual machine, then you can write Ruby code and run it. If your satellite has a Python virtual machine, you can run Python on it, right? Or your AMD processor, your Intel processor, your freaky deaky upcoming Apple processor, it doesn't matter as long as you have a virtual machine for that platform, as long as you have a translator that can speak your interpreted language on one side and output native language on the other side. And that's how computers work. Cool. So this is called like I would call this an execution stack. Built on the CPU, has these 4 key components, x86 instruction set, the idea of the clock, deciding how fast everybody moves. Clock came from buckets, turning constant flow into interval flow. We needed that because we wanted to do things on certain timings to run through. Talked about binary, octal, decimal, and hex as like different ways of representing on and off, right? And so hex is just a shorthand for representing a whole bunch of binary numbers, because writing out all these ones and zeros is hard. Explain where those ones and zeros could come from, like ideas of turning things on and off. We turn them on and off by using these teeny tiny switches called transistors. And all the heat and all our problems, like the transistor is like our greatest ally in that all the work happens through there, and it's like the weakness in that the size. One thing I didn't say is like part of how you make transistors cooler is you make them smaller. And so we talk about like the size of a process, like 3 nanometers or something like that is the smallest transistors that we can make at scale now. as you make them smaller and smaller, there's fewer molecules moving back and forth, so they generate less heat. You can pack more of them into the same space and yada yada. So then you get into like nano computing and all that kind of stuff. That's coming. That's coming. Power switch. Oh yeah, that was maybe like your takeaway. Circle means off, line means on, because of this. Hope one day you'll like building web apps is cool. And it's a good way to get a job and get paid and all that stuff. And once you have a job, then do something more. Like web applications, it's just like, it's fine. You can do lots of interesting stuff there. But there's like such a bigger world to computer science. You know, I hope that you'll like take some opportunity to dive into hardware and like hardware hacking, or diving into like compilers or native code or like anything. There's a big world out there. You're just going to see a Turing. You're going to see like a little pie slice of it. I hope you enjoy some things, and you can DM me on Slack if you have follow-up questions. And otherwise I'll let you get on with your day.
Well, thank you, Jeff. Let's take a break. Let's be back at 11:20 and we'll get started on learning to pair.
Learning to pair, the most important lesson.